Okay, so welcome back, and now we'll have the second part of the hybrid lecture by Dmitry Noshchenko.
Hello everyone, and so let's continue our lecture series about quivers and not homologies. So yesterday we have finished by defining the material generating series for a symmetric quiver. So just a quick recap. So we have a symmetric quiver, which is just a collection of nodes and arrows. So we allow loops, and the condition is that every number of outgoing arrows equals to the number of ingoing arrows, so the quiver is symmetric, but otherwise no other conditions. And for such quiver, one can define a generating function of the following form. So it depends on the vector of generating variables x1 up to xn, where m is the size of the quiver, and parameter q, which is called the motivic parameter. And this is expressed as a sum. Maybe I could have written a bit more explicitly. So this is the infinite sum, a formal series, summation over integer vector. So d1, dm is some integer valued vector. And right, so here we have minus q to power sum of Cij di dj, so quadratic form, and in denominator we have a product of q per hammer symbols, so we put q squares from d1 up to the m. So this is what we have in denominator, and all this thing is multiplied by this generating parameters, so x1 to d1 up to xn to dm. So let's maybe take a look at some examples. So the most basic examples, well, as you may guess, are M-loop quivers. So let's take a closer look at them. So M-loop quivers. So I'll draw it here. So basically, this is just one node and certain number of loops. So one can write immediately. So the simplest cases would be, of course, m equals to 0 and m equals to 1. And so in fact, these are special cases. And in this case, well, you will see in a moment why they're very special. So let's just write the motif generating function. So let's first write it in general for general m. So this would be just sum over one integer d from 0 to infinity. And here in exponent we have d square. Here we have d square d x1 power d. So where x1 is associated to this node. And yeah, well, as you recall that we have finished yesterday, we have shown the factorization formula. So the product form for a material generating series, and let's see how this product form looks for M-loop quivers. So in general, one expects that so this could be written in a product form as some infinite product. And we have here, well, maybe I can write just using Q per hammer symbols. more universal way. So this would be a Q-Pack hammer x to power, let's say, r, q to power s, q square. Maybe I should have put s plus 2, maybe. I think it could be actually written like in this way. So here we have, most importantly, this exponents omega, which are motivic dt invariants of a quiver, which are integer numbers. Yeah, and here we have from R and S running all integers. Oh, just a very little remark. So here R shall not be equal to 0. So in fact, we start from 1. Yeah, and yes, now the question is, so can we easily compute these omegas? And so surprising answer is that it is not so easy, even for such a simple, seemingly simple case of envelope quiver. And but however, in the case when m equals to 0 and 1, one can easily write such a product form. And so I will just write it below. So can check yourself that zero loop equals to 1 over single Q-Pack hammer. So it will be x q square infinity. Well, I forgot to define this infinite Q-Pack hammer, but it's like obvious thing. So we have x qn just as a product for n, oh, sorry, for k. From 0 to n minus 1, and 1 in principle can just set n to be infinite, so this product become just infinite. 1 minus x times q to power k. And yeah, so this is for zero loop, and you see that in fact, well, if you compare, so omega, in this case, we have only one non-zero omega, so only one non-zero dt invariant survives. And let me write, just for convenience, as a generating function of such numbers. So I will write it as a function of x and q, and coefficients would be numerical dt invariants. So in this case, it's just minus x. So minus x, meaning that here we have essentially Q-Pack hammer, which has so minus power minus 1, and here we have this coefficient minus 1. So numerical dt invariant equals to minus 1 in this case. And let's try the same for one loop. So it's also quite easy. So in case of one loop, this would be also one non-zero dt invariant, but this time it's this expression. So it's q times x, q square, this Q-Pack hammer, and here omega one loop of x and q. In this case, is q times x. And this q is essentially the coefficient of x inside this Q-Pack hammer. So this q. And yes, so numerical dt invariant equals to 1, but also since this dt invariants, they're in fact coefficients in front of x's inside this generating series, so these are in fact some functions of q. In fact, they're polynomials. And one can ask, well, similar question, of course, what happens if you have two loops? And can we easily derive this formula? But it turns out that for two loops, it's not that simple. Yes, of course, one can write like the usual way. We write using the sum form. So here we have this square, square. Any question or no? Yeah, but in this case, it turns out that omega is not a finite expression. And this is the simplest case where this dt invariant is non-trivial, in fact. And I cannot even provide you a nice like closed form expression for this generating function, but you can compute it term by term using recursion. So I will not go very much into these computational details, but let me just to give you some feeling of how it looks like. So I will just write some few terms of this generating function. So to loop. Yes, it starts like minus q square x plus, I'll just write a few terms, q4 x square minus q8 x cube plus some other terms. So in fact, yeah, so this does not sum to a finite expression, and this series do not terminate. And yeah, so now this non-trivial information again is encoded in these coefficients, which are DC invariants, and integrality essentially is a statement about integrality of coefficients in front of these terms here. So here we have coefficients like -1, +1, -1, and so on. But it's not always plus or -1, so you will encounter like larger numbers if you continue to compute the series. Yeah, so you can also see something interesting here. So recall that we have defined, in the previous lecture, we have defined framing of a quiver. So we have said that if you have a quiver Q with some adjacency matrix C, so then one can study the matrix C plus F, where F is some integer number. And one can ask if there is an easy transformation for dt invariant between such framed quivers, but it turns out that it is not that simple. Of course, this prototype example of one loop, when you add framing, you just add some framing here, so you add some number of loops again. And yeah, so you can see that going, for example, from one loop quiver where you have finitely many dt invariants, after framing, you obtain something which has infinitely many dt invariants, which is quite a non-trivial phenomenon. Yeah, so this is just some educational example, and so let's just keep in mind that one can compute using recursion term by term the dt invariance for M-loop quivers, and I'll just make a pause. Yes, so our next step would be something different, but we will get back to M-loop quivers very soon. So our next step is the operator form of the Quiver series. Um, Yes, so one can define. One usually defines the quantum logarithm function as a function of x and q, and this is just the infinite Kubock-Hammer. And so usually it's written psi of q, but I will erase q just not to repeat it everywhere. So I will just write psi of x and q. Oh, sorry. I have to actually just write. I will write just psi of x because q is already. Assume that this is depends on q. So now we define some operators. So we define operators xi of the following form. So this would be, so these operators, they essentially depend on the adjacency matrix of a quiver. The -1 to power cii q cii -1 xi y I. So I'll tell you in a moment what are this x hat and y hat are. So then follows the product j smaller than I, yj power cij. So the small xi and xj and yj, so they're obtain, so sorry, they obey Q commutation relations. So if you act, so this yj act as operators commuting with xi, so this would give delta I, sorry, q to power delta ij, xi, yj. And xi's, they are just identified with usual generating variables, so they're like classical parameters. And so now, how you think about it? So let's fix some quiver. Yeah, so let's say we have some data for quiver, which is basically given by adjacency matrix and the vector of variables, so x1 to xm. So this is our usual presentation for quiver. So now, in order to construct this operator xi, one has to choose, in fact, the ordering of the nodes of the quiver. And given that ordering, so as this adjacency matrix, and you have, of course, to choose this order here, like to make this labels. So then one can construct such family of operators. And these operators would not commute, but instead they would obey what's called the quantum torus algebra. Namely, if you commute xi and xj, so this will give you q to the power aij xj xi, where this aij is simply so it's either cij or 0. Yeah, if I is smaller than j, otherwise. Sorry, I did something stupid here. That's minus cij. Should be like that. Yeah. So all right. So we have a quiver. We have chosen the ordering of the nodes, and one can define a family of non-commuting operators, which depend on the quiver via this dependence on the quiver matrix entries here. And now, so the main statement would be as follows. So the main statement is that the motivic generating series of a quiver can be written in operator form as the normal ordered product of psi operators. But these psi operators, they essentially, so these psi's which are here, but we substitute instead of x, we substitute this non-commuting operator as defined here above. So this would be given by psi of xm, psi of x m minus 1, psi of x1. And these operators must act on identity, so just on one. And then just compute act by all operators and compute the normal ordered product, and one can redefine the motivic generating series in this form. Well, one can ask why in principle this is interesting, but you will see in a moment. But before that, so let me mention something else. So some interesting property of this quantum logarithm itself. So maybe I'll just write it below. So we have psi of x, but one can ask, well, so if you have two variables which q-commute, so x, u and v is v times u. So then if you substitute such variables into quantum logarithms, then to base the famous quantum pentagon identity. So this has been proven by Fadeev-Koshaev in 1994. And in fact, this identity has some interesting relation with quantum integrable systems. And this identity reads that if you have psi of u, psi of v, so then this is psi of v, psi of minus v times u, psi of u. So you have probably seen it somewhere, or maybe not, but yes, why this is called a pentagon, you can just draw it diagrammatically as a true pentagon, and you have a path which has 3 steps and the path which has 2 steps. So the one with 2 steps is essentially on the right-hand side, and with 3 steps is, sorry, the left-hand side, and the right-hand side is 3 steps. So in this picture, one can just draw probably I should write first v here, because we first act by v and then we act by u. So first act by v. So now, keeping this identity in mind, so one can ask, all right, so now we have this, but we also have this. And yes, so what does it mean in terms of quivers? So can we model this pentagon identity using quivers somehow? And the answer is yes. So I will show you in a moment how it's done. So maybe I can go below here. So in order to do that, one picks up a pair of quivers which look like that. So this is quiver Q, and we have a quiver Q prime, which is of this form. And well, we can just put some labels here. Got to put here x1, x2. Here I put different colors. So here I put x1 prime, x2 prime, x3 prime. So now if one follows the recipe as above for the motivic generating function, so let's just construct this x operator first. So for the first quiver, we have x1, we have x2, and this is just so in principle order is arbitrary. One can of course solve x1, x2. This doesn't change anything here. So this is q inverse times x1, and x2 would be q inverse times x2, and now times y1. So since we had a connection between x1, x2, and since x1 goes first, x2 goes after. So that means that when we compute operator associated to x2, and we take into account the arrow which goes from x1 to x2, and this amounts to adding this operator y1, which acts on x1. And similarly for q prime, we have x1 prime, x2 prime, x3 prime. Yeah, so this is q inverse x1 prime, q inverse x2 prime, minus x3 prime y3 prime. Yeah, so here again, we don't have any operators here. So since we don't have any loops, so these are completely disconnected, the nodes, and they don't have loops. But here y3 appears since it is a loop here. And yeah, so essentially what we can now write is, yeah, so we can assemble the generating functions by just writing like p q.
Is there a negative sign?
Sign, you mean this one?
Wow.
Yeah, so this sign, because here the number of loops is odd. So here you have, yeah, we had, I can just go up here. Yes, we have here -1 to power CII. Yeah, so this sign appears. Yeah, so maybe as an exercise, you can of course check that if you take this psi operator, so you will indeed recover the generating function. So this is so this acts on one, and then you take normal order. So I mean that you compute all, so you act by all the operators, and you push all the head operators to the right. And yeah, so for p prime, you have similarly the same, but with primes, with x3 prime, x2 prime. So it's very important here to keep order of the separators. So once you fix the order of a quiver, you can construct this size, but if you permute this size here, of course, you don't get the same result. So it is important that this numbering follows, because it follows essentially the definition above. As, I mean, this definition here. And so in order now to see the relation with the pentagon identity, one has to do some substitution. So one cannot simply say that this is what we want unless we assume that this is the assumption. So assumption is as follows. So we have x1, we have some identification. So x1 prime equals to x1, then x2 prime equals x2 as well. But then we have x3 prime, which must be identified with q inverse x1 times x2. And so the main statement is given that assumptions, we have the following identity. Which is analogous to quantum pentagon identity for the logarithm. So we have psi of x2, psi of x1 equals psi of x1, psi of here minus q, x1, x2, psi of x2. So essentially what we did here, we tried to, we used the fact that the psi operators obey the quantum pentagon as above, so this identity. And furthermore, we used the fact that, yeah, after such identifications, so these x variables, you can identify also the separators as well. So you see that x1 equalizes to x1 prime, x2 to x2, and well, okay, you see that not quite, right? Because we have here y1, but you can do a little trick, in fact. And this little trick, just to make this x1 and x2 prime to be equal, is to insert y1 here. So we can insert y hat 1, and since it acts on identity, so this is understood as, in fact, like acting on identity, computing normal order. So then this does not change anything, right? So by this tiny modification by hand, you don't change the result, but you make x2 equal to x2 prime. So now we indeed see that this is the pentagon. And yes, so now the question is, can we generalize this? So we have seen that such an identity holds for a pair of Quivers, but they're quite special. But can we make something similar, a similar statement, but for a pair of arbitrary Quivers? And the answer is yes. So I'm just thinking I'm going to erase that. And maybe I'll just erase the board. So here I'll just write again this pair of Quivers. So now we want to make it more general. Relation. And So one can note something here. So essentially the relation which was equivalent to the pentagon was the relation of removing the pair of arrows in one quiver. And yeah, here of course you have these two other nodes. And this removal of pair of arrows resulted in addition of an extra node with some extra loop here. And now one can define the more general operation, which we call unlinking. And this operation we denote by capital letter U and the pair of indices ij. So this ij would be the nodes of the quiver which we unlink. And this acts on a quiver Q, and one can write it separately as some modification of adjacency matrix. One thing, and second thing is, of course, modification of the vector of variables. Which I will write like this. Yeah, so let's first just notationally fix that. So in this example, what we had here, we have uij. Oh, maybe I can write like u12 uij. So we have u12 acting on the quiver, which is this guy, so 1 and 2. Yeah, so this results essentially, yeah. So how do I want to write it? Maybe. Yeah, I'll just write like notationally to make it completely clear. So we have uij acting on adjacency matrix first. So adjacency was just 0, 0, 1. Yeah, and then uij acting on the vector, and the vector was just x1, x2. Now we want to evaluate this, and the evaluation gives the modification of the matrix first. So then we have this matrix, right? And the vector of variables is changed. We have x1, x2, and the new variable is the Q inverse x1, x2. So this is how we want to present this previous example by just this new notation. And the generalization for an arbitrary quiver matrix would be as follows. So this is very direct generalization. So given a matrix C, so it would be C11, C1M, oh, CMM, sorry, so here C1M, C1M, and the vector of variables would be just x1 up to xm. So when do unlinking, we do some modification here. So we get uij of C would be, so this would be some blocks. So essentially the first block is of the same size. So then CMM, but here, and then okay, I need some still more space. So we need select some CII, and here we have CGJ, and here we have CMM, and here we have additional node which we append. So this was like the matrix of the previous size, and the extra node that we add here would have CII plus CGJ plus 2 CIJ minus 1. And by unlinking, we of course remove a pair of arrows between I and J. So all stays the same in this block, except from the connection, which was Cij minus 1 now. so we subtract 1, and yeah, so this was this whole block. And the new nodes here, they are arranged as follows. So we can divide them into groups. So one group essentially is this pair that was that has the index I and j. So here you have CII plus CIJ minus 1. So the pair which participates in unlinking, CIJ plus CJJ minus 1. So yeah, and the rest would be slightly different. So those will be 1i plus C1j and so on and so on. So we don't add this one. The rest will be units. And here will be CIM plus CJM. And analogously here. So this is the modification of the matrix, and the vector is very simply modified. So if you act by uij now on this vector, so then this just appends an extra node, which is of course Q inverse xi xj. So this is the general definition of unlinking, and now we can state a theorem. By Ekholm, Kucharski, and Longi. Somewhere like, yeah, so the theorem states that the generating function of any quiver equals to a generating function of unlinked quiver for any q. So in fact, this is not very hard to prove, but it's also not very trivial. And to see that, I think it was quite an achievement of Piotr and Tobias. So they just seen this relation, and it turns out to be very fruitful. So in the next lecture, I plan to continue study this relation. So I will show you many interesting properties which arise from such a relation. And after that, there will be some connections to knot invariance and some other invariance of three manifolds. So today, yeah, I think it's more or less what I wanted to say. So maybe I will just stop at this moment, and if there are any questions, I think it's quite the time.
Okay. So do you have some questions, or maybe there are questions on Zoom? Please unmute yourself if you want to ask a question. So Suraf, I noticed you unmuted yourself. Do you want to ask something?
Yeah, I'm not. It might just be a very stupid question. It's all new to me. So you wrote this pentagon identity with these operators. Just like my understanding of pentagon identity is that it's associated with a group, and the 60 symbols of the group satisfy a pentagon identity.
Mm-hmm.
So can these be interpreted in the same way?
So you mean 6J symbols? Or could we make a little bit more precise statement? I don't know. So what is the relation to 6J symbols?
If we, in the sense they satisfy a pentagon identity,
Yes, let
Is-
me just, as I raised, I'll just write it back. So you
Is-
say that if we have these and
No,
yes, so
I was
6Js there.
No, I was just wondering if this can be interpreted in the same way, or it's something independent and has nothing to do with the group.
I don't know the connection to the 6J symbols, but maybe there is a relation. So in fact, this identity, it is somehow related to Young Baxter. So it has this connection to some quantum integrable models, but for 6J symbols, yeah, I'm not sure. I don't know if it's the same or not, but
But these,
maybe if you
how does this relate to the Young-Baxter equation?
oh, it's also indirect a little bit. So it's called restricted. I think it's called restricted star triangle relation. So I can, yeah, I will not give you details, but I could refer to the paper, basically this original paper by Fadeev Kashaev. So they study these connections, but I just don't remember it like by heart.
So Rama, you say there is connection to 6J?
Yes, there are pentagon and hexagon identities which require some properties to be satisfied by the group. But I'm not sure how this will appear there. I have to see it from that perspective.
Okay.
But technically, we look at it, one is a trilinear relation of the breakthrough, which you can compare and see how the 6J symbols are related. And there is also another relation which involves viewing topological equivalence of the same unknot in two ways, and then you can try and get a relation which looks like the pentagon identity
Okay.
and the hexagon.
I remember that Elder Laragiver was mentioning, he mentioned once some pentagon and hexagon identity, but I think what he mentioned was not directly related to this pentagon, but I'm also not sure whether he mentioned pentagon and hexagon in the context of 6J. So
I cannot see it right away how this is happening. Probably I have to see the Keshav's paper.
Okay, I think we need to finish for today because this room will be occupied soon. So let's thank Dima again.
Yeah, thank you.
Oh, and maybe just quick announcement for all people that there will be 4th and 5th lecture on Monday, and on Friday we will give you exact. We'll tell about it on Friday as well, but we scheduled it for 1 p.m. on Monday. Right?
So Friday he will give the third.
Yeah.
Yeah. Friday there will be 3rd, and 4th and 5th will be on Monday at 1 p.m. And we will tell it again on Friday. Okay.
Yeah. Thank you, Piotr.
Thank you very
Thanks,
much.
everyone. We'll see you next time.
So this video will be out tonight.
Let me just